Hello, I'm Asli Celikyilmaz. It's a pleasure to be here and speaking about our recent work on embodied conversational agents. I will be speaking about the problem of teaching agents planning and navigation via cooperation. As a means of introduction, one of the areas I'm interested in investigating is how we might develop models that achieve deeper semantic understanding and generate language to fulfill tasks in human environments. We focus on building agents that can not only navigate to goal location, but also hold a coherent conversation and show some degree of understanding of the interactions. Understanding the semantics of language and communicating it to humans in a coherent narrative, which in my mind are one of the most important fields that NLP researchers are trying to excel. So the key component to a step towards this goal is by thinking about building AI systems that can communicate naturally with people. I think everyone here would agree that natural language is an ultimate API for dealing with a human. But secondly, we also need to teach the AI systems to learn deeper semantic understanding and semantic structures that are building blocks of a language. We would like to build computational models for representation, extraction, and generation of semantic information from structured and unstructured data, involving text and other modalities such as images, video, and speech. So this motivation brings us to one of the underlying goals of this work, which is learning to ground. In other words, how does language relate to the real world? So in natural language generation world, this can be explained with the problem of choosing the words to express data. For example, today's visual question answering systems or image or video captioning systems that are set to truly understand concepts or phrases, however strange they look, can map a visual concept like this, which is mainly about noun phrases, into correct words. We can also train models to map an image like this into actions or verbs, such as sleeping. Today's systems have very high accuracy in these tasks. However, when it comes to do reasoning, explaining a simple concept by combining them to form new language, for instance, even with today's advanced encoders, it can be a challenging task to learn to explain them coherently. To improve on learning better representations, generate better natural language, or learn to answer questions better, researchers have been focusing on grounding from different perspectives. There's a spectrum of research in this direction, but if I were to classify the language grounding efforts into categories, of course, I may not cover the whole research area in this field, but some of the notable grounding examples from speech, NLP, and vision world will be first understanding with language models and knowledge graphs. There's a huge research field on question answering models grounded in knowledge graphs and lately in language models as well. In more recent years, we have been seeing question answering models grounded in vision. For instance, the Clever dataset provides a platform to ask questions about rendered artificial photographs. Visual question answering is also another one, which is photorealistic environments, and you can ask questions like, what is the mustache made of? So these are real photographs, but again, just a single answer. So language generation community has also investigated grounding of generation in images in tasks like image captioning or visual storytelling. So we have some work in this area as well. So since 2018, there's also growing interest in visual language navigation work. So the core of which is grounding language description or instructions to physical spaces to make inferences, answer questions, or navigate. So on the left, we have room to room, where we have long, low-level language instruction, and we get new visual frames at every time step to infer navigation actions. The goal is to build intelligent agents to understand visually grounded language while navigating in photorealistic environment just to arrive at a goal node. Embodied question answering and interactive question answering usually get high-level questions rather than low-level language instructions. Embodied question answering is actually a non-photorealistic environment, while interactive question answering has a bit of a photorealism in the environment. So among these last three, the room-to-room has been investigated by many. Specifically, in visual language navigation task, an agent has access to the long natural language instructions that tells how to get to the goal location. So the room-to-room dataset has a simulator that lets the agent start from a location, observe panoramic photorealistic images to take actions at each time step, and to take some discrete set of actions. So we're going to do a really a short pathfinding. The actions are forward, turn left, right, tilt up, down, end. The goal of this task is to build to follow instructions in seen environments and test the agent's performance on navigating to a goal location in a previously unseen real-world setting. So the environments in room to room is interesting because these are real human environments and they include noise. As I mentioned before, visual language navigation presents some unique challenges. The first one of the major challenges is cross-modal grounding. The agent is usually spawned at a random location, then given an instruction, it is expected to follow the instruction and navigate to the destination. This requires the agent to interact with the environment and ground an instruction onto both the local visual scene and global visual trajectory. One of the other issues during training of visual language navigation agents is that the feedback is ill-posed. What I mean by that is that the success feedback is rather coarse because the feedback is provided only when the agent reaches a target position, while the reward function completely ignores whether the agent has followed the instruction or not. In addition, even a good trajectory that matches an instruction can be considered unsuccessful if the agent stops marginally earlier than it should be. In our recent work on visual language navigation, we trained an agent to learn to ground language instruction in visual context using reinforcement learning and self-supervised imitation learning. So our model enables to efficiently navigate in unseen environments. So I will tell a little bit about this work before I move on to conversational navigating agents. So the goal of our work is to ground the language instruction both locally and globally using reinforcement learning. So the agent has access to a full set of natural language instructions. It is put inside a building to start to navigate. So we build this reasoning navigator which generates a trajectory, which are these discrete action sequences, based on the history context, the instruction context, and the visual context. So the agent learns to stop either when it decides it reached the target location or a maximum number of steps are exhausted. Then the environment provides the extrinsic reward, which is simply measuring the success rate we talked about to optimize the navigator. So up until now, we have never forced the agent to follow the instruction. With our matching critique, which is trained with a cycle loss to determine to what extent the original instruction can be reconstructed from the visual trajectory, we can provide an intrinsic reward to the model, the navigator, to optimize the navigator together with the extrinsic reward. So this setting encourages the agent to respect the instruction, as well as it penalizes the path that deviates from the instruction. We train the reasoning navigator using supervised learning first, and then switch to reinforcement learning. Our model needs to also generalize for the unseen environments, which is something we found during our analyses. So up to now, we didn't let the model explore to unseen environments. To let the model explore the unseen environments, we built a self-supervision pipeline. We start with the text instruction, and our navigator generates sequences of actions. The matching critique receives both the generated trajectory and the natural language instruction and measures how good the alignment is between the instruction and navigation path. Among several of these navigators, we select the maximum ones and add to the replay buffer. Then we add this to our training dataset to continue training since no target location information is provided. No supervision from the environment is needed in this case. The setting of ours not only improves the performance of our model on unseen environments, but it also has a practical use. For example, it can facilitate the adaptation of domestic robots to deploying to new houses. So by exploring good trajectories in the buffer, the agent is in a sense doing self-supervision. This actually yields approximation of better policy that adapts to new environments. One last thing that I want to mention is this data scarcity. It's an issue in which several new research is actually trying to deal with using transfer learning settings by introducing language model pre-training, back translation, and things like that for visual language navigation tasks. In fact, there's been several work focusing on some of the issues I mentioned. So on one hand, it feels like with these new advanced transformer-based approaches, our back translations and other things, we're coming closer to applying recent advances in language understanding to navigation. But there's a lot of recent work that shows that such models often exploit shortcuts to game datasets without solving the actual tasks. This not only applies to visual language navigation, but also any grounding task in natural language processing. This actually caused a shift in visual language navigation towards more dialogue settings. So those limitations apply to teaching models to perceive the complex or compound actions in the real world and taking actions, making inferences, and reason about them. There's key challenges in dialogue-oriented visual language navigation tasks. One of the first is connecting language to vision. So the agent needs to decide what the meaning of the second door on the right is. Then comes learning when the agent should ask a question. Is it when any uncertainties arise? Also, how to provide the best feedback for the agent when it is in need for help to complete the task is an open research question. So the question now becomes, how does language relate to the real world, and can we solve this via cooperative learning and natural language dialogue? So in fact, adding dialogue as a component has made several of the earlier tasks discover and extract new information. So I'm going to use the same related work template, but this time adding dialogue. First yields the grounding language to knowledge graphs, which made easy with dialogue systems in human-in-the-loop scenarios. On visual question answering tasks, Clever has released Clever Dialogue. So they have the same type of initial questions from before, but the system needs to use the context and do co-references in dialogue context to answer the questions. So the questions are templated in this data set. Similarly, in visual question answering, the visual dialogues dataset had humans playing the game. So these are like human games, and we could say things like, what is the person doing as a question, and it requires you to look at the past context to figure out which entities are being referred to. So different from this work, there are very recent work that enrich the visual language navigation interactive agents so they can get simple advice from the users to complete the task. So the recent work has now shifted towards dialogue-like navigation, and in these settings, there is a navigator agent performing the actual task, and a guide, or an oracle, if you will, which is a second agent that guides the navigator by providing additional help. So in this direction, there are two recent work that enrich navigator agents with when to ask question capabilities, while the language to ask help is templated and under-specific, and that the language does not encode the navigator plan in most cases. So a natural next step is to build navigating agents that can communicate with the interlocutors in natural language and ask for help when needed in natural language and extract useful feedback to plan on their next set of actions to reach the goal location efficiently. We're going to talk about this in a minute. But before I talk about them, let's first look into some of the challenges of enriching visual language navigation with dialogue. So the visual language navigation with dialogue, the dialogues are turn-based. So there is a navigator and a guide helping the navigator with reaching the goal. So the navigator follows the instructions provided by the guide and asks questions when in doubt. So we categorize modeling the turn-based dialogue into 4 categories. The first one is deciding when the navigator should ask a question, generating navigator question, then generating guide answers to navigator's questions, and then lastly, generating navigating actions based on planning that it does given all the information provided in the context. So the first and the most adapted model is a sequence-to-sequence-based model that consists of a navigator that just takes actions given instructions. This is actually the room-to-room environment. Although not quite dialogue setting, the speaker-follower model introduces a creation of a speaker model by augmenting data that provide additional instructions. So these could be considered, in a sense, answering navigator questions. In a more recent work, the navigator decides when to ask questions, but do so as simple as like help enough flag with oracle responses. And in another recent work, the navigator decides when to ask questions, but the oracle only provides the next plausible step. So in these models and others that I'm listing here, no questions are generated by the navigator to converse in turn-based dialogue, no natural language questions, which enable natural cooperation between agents with the goal of replacing the guide with humans in the future. So in the next, I will talk about how we model such an agent. Okay, so in a recent work, Thomas and et al. has restructured the room-to-room environment to introduce dialogue component and release a new dataset and task called Vision and Dialogue Navigation last year. Visual dialogue navigation is a task in which a navigator and a guide cooperate to find a destination. It builds upon the two-agent dialogue dataset, cooperative visual dialogue navigation dataset, which was introduced in Thomas and et al. The idea is that a navigator and a guide human agents collaborate to find a goal room containing a target object. Both the navigator and the guide view the same navigation environment, such as this, only the navigator controls the search and trajectory. At the start of the episode, a hint is provided, which is visible to the navigator and the guide. The navigator moves in the environment, and the guide observes the navigation steps. Such as this. The navigator then comes to a point where cannot make any decision, so it decides to ask forward or right from here. After the navigator asks the question, the guide sees the next 5 observable steps, which is closest to the goal location, and communicates these 5 steps to the navigator in natural language, says turn right, go forward, and take the stairs up. Then the control switches back to the navigator, and it continues to navigate until it comes to a point where it doubts the next move should be. So you're seeing here the navigator's steps while guide observes. And then in here, there are a few steps it could take, but it doubts. So what it does is, it asks another question. Should I go straight? Then the control goes to the guide again, and it again observes the next 5 steps. These are closest to the goal location. And then it communicates it back to the navigator. It says, yeah, go straight towards the desk, walk past by the glass walls on the right. And then the navigator takes this and then decides on, makes a plan and decides on what action it should take. And this continues, the conversation continues this way. So the idea here is to replace humans with machine learning agents to see if we can actually teach them to communicate in natural language and still hold a coherent narrative, but also help each other to reach a goal location. By doing so, our work becomes the first to train 2 agents jointly on multi-turn dialogues where agents both produce and consume task-relevant language. So in this work, we sort of avoid learning to decide on when to ask a question. Instead, we used a fixed heuristic. So we have 3 goals in this work. We build a system in which agents will cooperatively search through the space of dialogues to efficiently perform embodied navigation. So this case is regarding training 2 agents, a navigator and a guide, in which the navigator is given a target like a key and uses this information to execute on a sequence of actions, while the guide, having the partial observability of the environment, helps the navigator to get the goal location. We are also going to have the navigator and guide to speak in natural language by designing language decoders to learn to ask and answer questions in natural language. Also, just like in theory of mind, which posits that for efficient communication, people both model listeners' mental state and effects of their actions on the world, we're going to introduce recursive mental model of a conversational partner, the navigator, which will spawn instances of itself to simulate the effects of dialogue acts on navigation. So first, we start with a navigator agent that moves through the environment. So navigator first receives a hint, not a full instruction. The goal is to navigate to a place where this object might be. So at any given time in the episode, the navigator has access to the previous observations, the hint it received from the environment at the start. Given this input, it decides to take an action among 6 discrete actions: forward, left, right, etc. So it either stops when it is closer to the goal location or exhausts a maximum number of steps determined by the environment. When it reaches the end, it receives a reward. The reward is a goal process, which is measured in meters. So the distance reduction between the navigator agent's starting position and ending position with respect to the goal location. On top of the navigation property of the navigating agent, we enrich it with a question generation capability. So the questioner is an encoder-decoder model which takes in a sequence of images and the current viewpoint where the question is asked and the target object, and it decodes using a decoder by attending over the input images to predict the sequences of tokens that make up the question, such as, should I go back to the room I just passed or continue on? To generate answers to the questioner, we have a third model, which is our second agent, which we refer to as a guide. So the guide receives the question, and together with the images of the next 5 steps to the shortest path, the navigator, shortest path to the navigator should take towards the goal. It encodes them first, then it decodes the language tokens as the answer to the question, as if it would be produced by a human agent. And it uses this sequence-to-sequence model. Both guide and the questioner uses the similar models. So we introduced the recursive mental model agent, which is RMM, in which the navigator, questioner, and guide learns from each other, and each rolls out possible dialogues and trajectories. So our first navigator agent, it navigates n steps, each maximum length of, say, L steps. And then the navigator decides to ask a natural language question and rolls out different questions. So these questions are all natural language, the ones that we saw before. Then, given these questions, the guide responds with n different answer sequences. Remember, these are long instructions of the next 5 steps, that is, closest path to the goal location. Given the history and the recent answer from the guide, the navigator rolls out n different steps, and this process continues. And the recursive mental model of ours is an RL-based model, and for each sample generation, to span a new dialogue and corresponding trajectory to the goal, it allows this type of sampling. So the dialogue that leads to the most goal progress is followed by the agent in our setting. So we train this using an actor-critic policy gradient using goal progress as a reward. So let's check some quantitative results when applied this on visual dialogue data set. First, we present dialogue results from our RMM agent compared to a sequence-to-sequence baseline and a sequence-to-sequence without a data augmentation baseline. So data augmentation adds additional and possibly noisy training data for the model with the goal of better generalization. So the goal progress evaluates the quality of the inferred navigation trajectory. So we report results on test data of seen houses, which are novel dialogues in houses which have been seen before by the model. Also, we're reporting results on the test data of unseen houses, which are dialogues taking place in novel houses. So in both seen environments and unseen environments, our model, recursive mental model based agent, make the most progress, as you can see from these images. So we designed our recursive mental model such that it introduces RMM, so it introduces a new language by exploring the environment and generating dialogues. So we use an RL laws to update the language generation models based on the most successful dialogue. So we test this property by investigating the log frequency of the generated text compared to the real human conversations. We noticed that our RMM model can actually generate new language and produces over 500 unique lexical types, which is actually closer to the nearly 900 types generated by humans. So I'm also showing a plot, a dialog plot for baseline sequence to sequence and sequence to sequence with data augmentation compared to our RMM model against goal progress. So the RMM consistently outperforms the other two agents in terms of goal progress, as you can see from this image. We see an increase in progress for, as you can see here, the first 10 to 15 questions before RMM levels off. By contrast, baseline and the data augmentation agents exhibit a shallower curves and fail to reach the same level of performance. So as you have seen in this talk, the agents are trained on human-to-human dialogues of natural language questions and answers from cooperative visual dialogue navigation dataset. So individual questioning and answer exchanges in this dataset could be really underspecified and rarely provide simple step-by-step instructions like go straight or turn right. So instead, these exchanges relied on assumptions of world knowledge and shared context between the agents, which actually manifest as instructions which are rich with visual linguistic core references, such as should I go back to the room I just passed or continue on, or things like that. So none of the trained agents actually learn to stop talking, but our maximum trajectory length caps them at 20 exchanges, while humans average on like 3 exchanges with a long tail, actually. So long trajectories might actually improve the performance, but are computationally expensive on the other hand. So, so better stopping functions is an important next step for our work. So briefly, today we can actually train agents to parse natural language instructions to fulfill simple tasks and learn to ask questions when in doubt. And two-agent task paradigm to teach a navigation agent to communicate with other interlocutors in natural language is, in my opinion, the next step towards to computer communication and dialogue grounded in human environments. So we presented an RL-based formulation that suits best for visual language navigation task in which the navigator agent can learn to plan ahead to efficiently navigate while being guided by another human or an agent. We hope that this task and paradigm will actually inspire future research on learning agent-to-agent, task-oriented communication with an eye towards human-agent cooperation and language-guided missions. With that, I would like to leave you with 2 recent papers that I try to cover today. I'll be happy to take any questions online or offline. Thank you.